Draw the products for each of the following reactions disregarding stereoisomers. Now this is a reaction of an alkene with NBS. What is NBS? NBS is N-bromosuccinimide, which is going to do the allylic bromination. So if we consider these two carbons are sp2 hybridized, and therefore they are vinylic carbons. But this carbon is allylic carbon, and you can see that it's adjacent to the vinylic carbon, and it is sp3 hybridized. Okay, now what's going to happen in the first step is it's going to create as an allylic radical. Let's draw the allylic radical. So it's going to create this allylic radical after the hydrogen has been abstracted. And then it can react with a bromine molecule. So where the bromine is going to get added here. So this would be the product that will be obtained. But since we know that the allyl radical can be resonance stabilized, we can also have another product where the pi bond is going to break and it's going to lead to the formation of another radical. Okay. So this is a new radical that has been created, and this can further react with bromine to form a product. Okay, let's go on to the next reaction. What is the product that will be obtained for this reaction? So this one is a cycloalkane, cyclohexane, and if you take a look into this, there's only one hydrogen, one type of hydrogen, right? So all of these hydrogens that are in here are exactly one and the same. So replacing any one of those hydrogens is going to give us exactly one product, which is going to be this. Let's go on to this reaction right here. Now for this reaction, there is going to be different products that will be obtained. There will be 4 different products that will be obtained because there are 4 different hydrogens. So this is one type of hydrogens. We know that there is a hydrogen here. That's one type of hydrogen, and we also have 3 hydrogens here. That's one type. And then we have one hydrogen here. We have 2 hydrogens here and 2 hydrogens here. Right? These 2 positions are equivalent. So whether you replace this hydrogen or this hydrogen, it's going to lead to exactly the same product. And similarly, these 2 hydrogens are same. So on the whole, you have 4 different hydrogens. And replacing each one of those hydrogens is going to give 2 different products. So here are the different products. So this is one type of product. And this is the other product. So these are the 4 different products that you'll be getting. And for this reaction right here, there's not going to be any product for this reaction since you do not have any heat or light, right? So if you have a heat or light, then probably it would be a different scenario where one of the hydrogens will be replaced by chlorine, right? But since there is no heat or light for this reaction, light employed, then it's not going to lead to any products. So there's no product for this reaction. And taking into consideration this reaction is basically a radical substitution reaction where one of the hydrogens need to get replaced by bromine. And bromination is very selective. And since you know that there is a hydrogen that can be replaced by a bromine here, and since the tertiary alkyl radical can be created much faster than the primary and the secondary, this is the hydrogen that's going to get replaced with bromine. So the product here would be this. Let's do question number 3. Draw the major product for each of the following reactions and disregarding stereoisomers. Now NBS, both of these reactions are with NBS. NBS is going to do the allylic bromination. So if you take a look into this, there is only one allyl position. So obviously that is the position where the bromination happens. There are two hydrogens here. One of the hydrogens will be replaced with the bromine. So the product here would be this. Let's take a look into the next reaction. So here again, if you take, there is only one allylic position. So if you consider this double bond, this carbon, so this is your allylic carbon. So one of the hydrogens in there is going to get replaced with bromine. So the product here is going to be this. Propose a mechanism for the formation of these products. So here you have a bicycloalkene which has been reacted with NBS to give the two different products. We need to draw the mechanism for the formation of these two different products. Now NBS is again going to do allylic bromination. So this is your double bond. So let's find out the allylic carbons. So this is your allylic carbon. If you consider this as carbon number 1, this is your third carbon. That's an allylic carbon. And if you consider this is carbon number 1, this is also your allylic carbon, right? But both are equivalent positions. Okay, so with the use of NBS, it's first going to create as an allylic radical. Let's draw the structure of the allylic radical. Okay, so this is our allylic radical. Whether you have the radical here or here, it's one and the same, right? Okay, and the next case, the Br radical will come here together to form the bond between the carbon and Br. Okay, so that's going to lead to the formation of one of the products. Okay, which is this. This is the same as this. Okay, now what happens here is there is a possibility that this allyl radical can be switched to, can be resonance stabilized with another radical. Okay, let's draw the other resonance contributor for this. This pi bond is going to break, and this is all going to come together, and there is going to be a new radical on this carbon. So here is the new pi bond that's been created, and you have a new radical here. Now the bromine radical can come together with a carbon to form the bond. So this would lead to this product. Let's go on to question number 5. Draw the alkyl halide that would be obtained in greatest yield. So for all of these reactions, for all of the radical reactions, it's important to identify or important to sort out the different reactions. So you have here an alkane that is reacting with chlorine in the presence of light. So this is basically a radical substitution reaction. Whereas this one right here is a radical addition reaction, because whenever you have a double bond and you reacted with HBr in the presence of peroxide, it's going to be a radical addition reaction. You cannot add anything in here, right? Like, because this is already this has got only single bonds. You cannot add something to a single bond, but you can add here. So therefore this is going to be a radical addition reaction in the presence of peroxide. So this reaction is radical substitution reaction, where one of the hydrogens is going to get replaced by the chlorine. Okay, so for this reaction, if you take a look into this, we'll find the number of different hydrogens. So these hydrogens are one and the same, right? But you have only one hydrogen, which when abstracted, is going to lead to the formation of a tertiary radical. Now, using the probability and reactivity together, so you have 9 hydrogens, which can lead to the formation of the primary radical, and the reactivity of the primary radical is 1. So that's going to be 1. So this is with respect to the product. So this is when, like, if you get this as your product, where you replace one of the hydrogens with the chlorine, one of these red hydrogens with the chlorine. But you can also get another product where you abstract this hydrogen and replace it with the chlorine. So if you do that, then it's going to result in this product. And the probability times reactivity is going to be 1 times 5, which is going to be 5. So on the whole, when you add these numbers together, it's going to be 14. So the percentage of this is going to be 9 by 14 times 100. But here it's going to be 5 by 14 times 100. So obviously, this is the major product that will be obtained. So that's the major product that will be obtained. For the next reaction, if you take a look into this, this is going to create the bromine radical, right? Hb on the presence of peroxide is going to create as a bromine radical, and this bromine radical will get added to the double bond. Now, which of these double bonds will get the bromine radical? Now, that is going to depend on which radical will be created, like which one of these is going to create a more stable radical. So if the Br radical is going to get added to this double bond, then it's going to create as a tertiary radical, right? So let's say that this Br is getting added to this carbon, then it's going to create as a tertiary radical, right? So here is your 7-membered ring structure, and the Br got added here, and your CH3 is still here, but this is going to be your radical, and you still have this double bond. And in the next step, this radical will abstract an hydrogen from the HBr to form the product. So this would be the product that will be obtained. Starting with cyclohexane, how could the following compounds be prepared? So let's draw the structure for cyclohexane first. Here is the structure for cyclohexane, and we want to convert this into an ether. So if you want to have an ether, then definitely we have to do a nucleophilic substitution reaction at some point, right? Where this, if you take OCH3 as a nucleophile, and if we have something like a leaving group, then it can leave, right? But how are we going to put this halogen on this cyclohexane molecule? Okay, so if you start with the cycloalkanes, or in general alkane, the only reaction that you can do is radical substitution reaction. So let's do that. So let's do bromination here, and that's going to lead to the formation of a bromocyclohexane. Once you get the bromocyclohexane, we know that we can do the elimination reaction on this. Okay, so when you say elimination, it's going to create as a double bond, like create as an alkene molecule. So for that, we are going to take a bulky base such as tertiary butoxides. Tertiary butoxide. And you take the corresponding solvent. So this tertiary butoxide, being a base, it's going to go abstract this hydrogen, thrust this bond to form a double bond here, and the leaving group is going to leave. So this is basically an E2 elimination reaction. And it's going to put a double bond here, right? And in the next step, we can do the allylic bromination, right? Look into this. So we need to have the methoxy group in the allylic position. So if you consider this is 1, 2, 3, this is a place where you want the methoxy group. So for which we need to put a bromine on this part, right? For which we can definitely do the allylic bromination with NBS, which is going to give us this. And once you have the bromine in the right place, then you can simply do a nucleophilic substitution reaction with methoxide ion, and that's going to give us the product. Let's go on to the next reaction. So So here you have a cyclohexane molecule on which we have to put an hydroxy group and as well as an OCH3 group. How are we going to do this? Again, starting from cyclohexane, we cannot do any reaction other than the radical substitution reaction. So we'll start with cyclohexane. And we will do the radical substitution reaction. That's going to give us this. Okay, once we have this, then we have to do the elimination reaction like we did in the previous question. So we always need to use a bulky base. The bulky base will definitely do to the elimination product rather than substitution, right? So that's going to put the double bond here. So the bulky base is going to go abstract this hydrogen. And once you have the double bond, what reaction can you do here in order to have the two oxygens? Yes, we can think of an epoxide ring structure. Like once we form the epoxide ring, then we can use another nucleophile to break open the epoxide ring structure. And so we will take peroxy acid. Once you have the peroxy acid, it's going to get converted into an epoxide. Once you have the epoxide ring, you can react it with methoxide. That's going to make a nucleophilic attack on this molecule. And remember, this is going to always come in a direction that's opposite to that of the leaving group, like the opposite to that of this ring structure. Okay. Therefore, it is going to give us two different enantiomers. And from there, you can isolate the one that you want. Using the given starting material and any necessary organic and inorganic reagents, indicate how the desired compound could be synthesized. So how are we going to synthesize this molecule? Whenever you want to create a cyclic structure from an acyclic molecule, you want to have the nucleophile and the leaving group present in the same molecule. Now we already have a nucleophile. This can be converted into a good nucleophile provided we abstract this hydrogen, right? But how can we have a bromine here? We need to have a bromine here because if you take a look into this, this is a 5-membered ring structure. So you have 5 atoms in here. So 1, 2, 3, 4, 5 atoms. So only if you have a bromine here, you can do the nucleophilic substitution reaction. Now, so think about all the reactions which can lead to the formation of, which can put a bromine in one of the carbons. So we can do if we do the HBr, just simple HBr addition, electrophilic addition reaction, it's going to follow Markovnikov's rule where the hydrogen is going to get added to this carbon and the Br will get added here. But that's not going to lead to the formation of this product, right? So what we have to do is we have to do the HBr with peroxide. If we do it with peroxide, then obviously it's going to follow the anti-Markovnikov's rule, right? Where the Br is going to get added here and the hydrogen is going to get added here. And in the next step, you have to abstract this hydrogen, for which you will be using NaH. NaH is a powerful base which will grab this hydrogen. So this is going to, the hydroion will go and grab this hydrogen, break the bond between oxygen and hydrogen. Okay, and that's going to lead to the formation of this intermediate. And once this is formed, this is going to do a nucleophilic intramolecular nucleophilic substitution reaction, which is taking place in the same molecule. When you say intramolecular, it's taking place within the same molecule. You have the nucleophile. So this is your nucleophile and this is your leaving group. It's exactly in the same molecule and it's going to lead to the formation of this product. Write the products for the following sequence of reactions. So here you have an alkene which has been reacted under several steps to get the product. Okay, so we have to find the products at each one of these steps. What happens when an alkene is reacted with chlorine? It is going to give us a vicinal dihalide, right? So let's draw the product here. So in the presence of chlorine, it's going to give us a vicinal dichloride. Now, if you want to, you can actually draw the product with the stereochemistry. So here is one of the products. The other product will be like this, right? And the two chlorines will be added in the opposite direction, in antiposition. Okay, so in the next step, so this is the product that is formed in the first step, and the next step, what's going to happen is it's going to react with it is being reacted with three equivalents of NaNH2 in the presence of NH3 ammonia. But what's going to happen here? The NH2 minus is going to act as a base, abstracting one of the hydrogens. So here there are two hydrogens and a hydrogen here. The NaNH2 is going to act as a base, which will abstract one of these hydrogens. If this is the hydrogen that will be abstracted, the chlorine from the adjacent carbon is going to leave, leading to an elimination reaction. So let's say that this hydrogen has been abstracted, this bond is going to kick in here, and the Cl is going to leave. That's going to put the double bond. And you still have two hydrogens on this carbon. Now this is just with one equivalent of NaNH2. You can, with the second equivalent of NaNH2 followed by NH3, it's going to do the same thing again. This is also another elimination reaction, where now this is the hydrogen that would be abstracted. And it's going to put the pi bond here, and the Cl is going to leave. It's going to create a triple bond now. Okay. Now with the third equivalent of NaNH2, the acetylene hydrogen will be abstracted. So this hydrogen will be abstracted, and it's going to create as an acetylide ion. So that would be the acetylide ion that will be created. Remember, you have the carbon here. Okay. So once the acetylide ion is created, in the third step we are going to react with CH3. So where a nucleophilic substitution reaction takes place. So this is going to act as a nucleophile onto this electrophilic carbon, and the I minus is going to leave. So this is one of the ways to form a new carbon-carbon single bond. So once you have this compound, then in the fourth step it is being reacted with excess of hydrogen in the presence of platinum as a catalyst. So this is a strong reducing agent, right? So which means it's going to get all the way to the alkane. The triple bonds are going to get hydrogenated into an alkane. So let's calculate the total number of carbons we have. 1, 2, 3, 4, 5 carbons. So it's going to lead to the formation of pentane. Okay, so this is with hydrogen platinum catalyst. Okay, and the last step, which is this fifth step, it's been reacted with bromine in the presence of light, where it's going to lead to the formation of lead to different constitutional isomers. So this is where we're going to find the different types of hydrogens. So these two hydrogens are one and the same, and abstracting any one of these hydrogens is going to give us, and replacing with bromine is going to give us only one product, right? So, and similarly, these two hydrogens are one and the same. And this hydrogen is another type. So there are totally three different types of hydrogens. But which one would be abstracted to give which one would be replaced with bromine to give the product? Bromination is very selective, but it's going to lead to only one product. So here, when you abstract these hydrogens, that's going to lead to the formation of the primary radical. But these ones, it's going to lead to the formation of the secondary radical. But these two hydrogens are different, right? When you abstract the red hydrogens, obviously the probability is higher. Therefore, it's going to lead to the formation of um, the product with bromine here or here. Either way, it's going to be exactly the same product because there's some side of symmetry in the molecule. Okay, so the product here would be this, and you will also form the corresponding enantiomer. Because remember, the radical is also planar, more like carbocations, so they can form two different products. And it's a racemic mixture. Let's identify which of these radicals is more stable. Let's take the first one. This is a primary radical, right? So this is a primary alkyl radical. Let's go on to the second one. This is a tertiary alkyl radical. And this one right here, this carbon is allylic carbon, and you have a radical, you have a free electron on it. So this one is a secondary radical because you can imagine that there is a hydrogen attached to it. Secondary allylic radical. And this one right here is a tertiary allylic radical because you do not have any hydrogen on this carbon because it already has got 3 bonds. And this carbon is an allylic carbon because this is an sp3 carbon which is adjacent to the vinylic carbon. So this is a tertiary allylic. So between the tertiary alkyl and the tertiary allylic, which one is more stable? Obviously, it's going to be the tertiary allylic because it can be resonance stabilized. So this is the most stable radical. Each of these reactions occurs during the free radical chlorination of methane. Which step corresponds to the first propagation step of the reaction? Now let's identify the first propagation step from the list given here. Let's take a look at the first reaction. The first reaction is basically an initiation reaction where a chlorine molecule has been broken down into 2 chlorine radicals. So this is definitely not the answer. And this option B is also not the right answer because this is a chain termination step where the 2 radicals combine together to form the molecule, right? In a propagation step, you need to have radicals on both the sides. You need to have radical on the left side and as well as on the right side. So obviously these two could be propagation step, but the question asks for which one is the first propagation step. In the first propagation step, you still have the methane. So this is the first step, whereas this is the second step. And both are propagation step, which is where one radical has been converted into another radical, and that radical is going to propagate the chain. Okay, so the right answer here is going to be this. At which of the indicated positions would the bromine radical react at the fastest rate? For which we have to find out which of the positions will have the most stable radical. Okay, so at position 1, so if I'm going to have a radical here, then it's more like a vinylic radical. The vinylic radical is not even stable, so definitely that's not going to be the right answer. So here, if it's going to create a radical, it's going to create as a primary radical. Here, it's going to create as a secondary radical. But here, it's going to create as an allyl radical, right? So if I'm going to pull the hydrogen here, it's going to create as an allyl radical. Secondary allyl radical, which is definitely more stable. And therefore, the right answer here is going to be 2. What is the key intermediate in the following reaction? Now here we have a reaction. We have an alkene that is reacting with HBr in the presence of peroxides. Now, what kind of intermediate that is obtained in the radical addition reaction? This is a radical addition reaction where the HBr will get added to the double bond in the presence of peroxide. So there is definitely not going to be any carbocation intermediate because in a radical addition, there is only radical intermediate. So you can also avoid this one because this is a radical anion. So in the first step, what's going to happen is the Br radical will be created. And this Br radical will add to the double bond to create a radical. So let's say you have the Br radical. The Br radical will add to this carbon, to one of the carbons, and here both the carbons are equivalent. So if the Br is going to get added to this carbon, then you will form the radical here. You will form the radical on the other carbon. So this would be the product that will be obtained.